Hi, are you there?
Yes, sir. Yes, sir.
Yeah. My end actually network is disconnected. I don't know the reason for that. Okay, sorry for the interruption. Yes, I hope that you are able to see the screen, right?
Yes, sir. Yes.
Okay. We are working with this dot, right? That's dot, right? That's dot C. Yeah. When you look at this particular piece of code, what can you see? You can see that the rank 0 is responsible to allocate the memory and store some random values to that particular global array. After that, what are you going to do? Okay. Here, what are you going to do is this global size. We are passing this particular global size to all the processes because while executing this particular program, we should all the processes should have some idea about global size. That is why we are passing that particular one. Next one is local size. Local size means how do we get the local size? Local size, when we divide the global size with number of processes, we'll get the local size. That means each process is works on that particular number of elements. Each process work on that particular number of elements. Next one is local data. This particular we are using this particular local data to store to sort the given list of elements. Okay. You suppose if we load some data into this particular array, okay, then we can sort but that particular data uh, uh, independent of each other. Each process can sort its own local data. When each process sorts its own local data, later we systematically merge their data to get the sorted list. To get the sorted list. Okay. After that, when you look at this particular MPI underscore scatter, what are we doing here? When you look at this particular one, this data is the global data. We are scattering this particular global data to this particular local data, this particular local data. So each process gets this many number of elements, local size this many number of elements. Type of that element is MPI underscore int. Which process is responsible to perform this particular scatter operation? Process 0 is responsible to perform that particular scatter operation. After that, what are we doing here? We are performing merge sort operation on local data. That means we are calling fetch sort on the local data, right? So each process can sort its own local data. Okay, when each process sorts its own local data, after that, what we have to do? Uh, Here we are going to gather that particular local data and store it into that particular sorted array. Okay. Now we have different chunks of sorted sublists. Okay. To get the original sorted list, what we have to do? Again, we have to apply some other procedure on the top of it. Okay. Now we are going to execute this particular one. Okay. When we execute this particular one, here there is a simple method is there. Vi test script 4 dot. Okay. Vi test script. 3 dot. Okay. Let's start. Okay. Right. Yeah. Here, when we look at this particular one, here what can you see? Here you can see that MPI run NP stands for number of processes and $1. That means we are passing the argument at runtime. Okay. We are passing that particular number of processes at a runtime, right? How can we pass that particular one? Okay. That means S batch, test script 3. Okay, we are performing this particular one with the help of two processes. Okay, where is the output? Actually, output is going to be stored in that particular output file 3315. Okay, how to get it? Cat outputs MPI underscore job 3315 3315 dot out. Here, what can you see? Here, actually there is a global data, and global data we perform that particular one, this med sort operation with help of two processes. Here, what can you see that? You can see that these are the first 50 elements. First 50 elements are in sorted order, and next 50 elements are in sorted order, and next 50 elements are in sorted order. What is our objective? Our objective is we have to merge these two sorted lists into a single list, right? To merge those two sorted lists into a single list, we have to perform something on it, right? What we have to do? We have to perform some logic. Okay, we have to write some logic here. If you write some logic here, then we'll get the entire sorted sublist. Entire sorted sublist. How to write such kind of logic? To write such kind of logic, I implemented little bit extension of this particular simple merge sort. That is merge sort with extension. Here, what can you see? Here you can see that. Here you can see that. Okay, this is the logic. This rank 0 is responsible to merge those two sorted list. Okay, here actually till this particular point we are going to store that sorted sublist into that local data or sorted data. After that we are going to merge those sorted data, right? How are we going to merge those sorted data? We are going to merge those sorted data with the help of the simple logic. Then we can get the entire sorted list. Okay, here I consider the global size is 10 power 9. Instead of 10 power 9, I would like to show the execution for 100 elements. I would like to show the execution for 100 elements. For 100 elements, definitely I can comfortably print that particular those 100 elements on the screen. Okay. Yes. How can we compile it? To compile this particular one, first of all, we have to load, right? Okay. Module load GNU8. Next one is module load open MPI3. Okay. Again, I did a mistake. No problem. Now we are going to compile this particular one. MPI CC medsort extension.c -o medsort extension.o. Successfully compiled. Now we are going to execute this particular one with the help of test script 4. If you look at this particular test script, we are passing this particular one as an argument. Okay. Now S batch test script. No, sorry, not S batch. What can you see here? You can see that. Okay. Uh, are you with me?
Yes, sir.
Hello.
Yes, sir.
Okay. Again, it is disconnected. That is the problem when we work from the remote location. YQVCQPP. CD, MPI, okay, S batch, S batch, test script 4.sh. Here number of processes 2. Yes. How can we see the output? Cat outputs MPI job 3316 out. Now when we look at this particular simple output, okay, all these numbers are in sorted order, right? All these numbers are in sorted order. Okay. When we look at this logic, when we look at this particular logic, what what I did, okay, okay. Till this particular point is very pretty much simple and straightforward. Okay. After we gather, we can have two sorted lists. Okay. So that means in the redundant list, first part is in sorted order and next part is in sorted order. We have to merge those two sorted lists into a single sorted list. For that, again, I considered this particular piece of code. This particular piece of code is responsible to merge those two sorted lists into a single sorted list. That is the beauty of this particular one. Now we are going to check the execution time of this particular one. Let us see. We are going to solve the problem of size. Here number of things is 10 power 5, 10 power 6, 10 power 7, 10 power 8, 10 power 9. Okay, we cannot print 10 power 9 elements on the screen. Let us assume that we'll get the correct output. I would like to comment this particular one. Okay, when I comment that particular one, now I'm going to execute this one. How can I compile it? I can compile it module module genuine load. How can I compile it? MPI CC match sort extension dot c minus o match sort extension dot o. Okay, now it is successfully compiled. Now I'm going to submit that job. S batch test script or right. Okay, here we are going to solve this particular one with the help of one process. Okay, SQ till it is running. Because size of the problem is big, right? We are going to sort 10 power 9 elements. We're going to sort 10 power 9 elements. Yes, still it is running. We're sorting 10 power 9 elements, still it is running. Let us see how much time it is going to take. Still it is running. Oh, still it is running. It is taking this much time. How many elements we consider? Power 9 or 10 power 10? Any guess? Right. Okay. Yeah. Let's sort session.c. How many elements are there here? Let's see. Yes.
It's 1 billion.
1 billion, right?
Yes.
Supposed to supposed to terminate, right? Still it is running.
We can tail the output, sir.
Okay. Are we going to print the entire list? No, we are not going to print the entire list. But we are sorting with the help of one. Okay. If that is the case, how can we cancel that particular job? If that is the case, how can we cancel that particular job? Still it is running. So yes, cancel job ID 3317. Okay. Now if you check it, nothing is there. Nothing is there. Okay. Are you with me? Suppose if there is any problem while executing that particular one, we can cancel that particular job with the help of the command yes cancel. With the help of the command yes cancel. Okay. Similarly, we can perform the matrix multiplication. Matrix multiplication. How can we do the matrix multiplication? If you look at this simple logic, this function is responsible to multiply two matrices. To multiply two matrices. Here in this context, what can be done? Okay, here we can do is first one is we can scatter the matrix A across all the nodes. Next one, here we can broadcast matrix B to all the nodes. When we broadcast matrix B to all nodes, that means that matrix B is available at all nodes. Okay. After that, whenever we perform this particular matrix multiplication, we will get, actually each process is responsible some number of nodes in the resultant matrix. Okay. Later, what we have to do is we have to perform a gather operation on that particular one. When we perform the gather operation, we are going to store the entire result in that particular matrix C. Okay, in that way, we can perform this particular matrix multiplication with the help of MPI program. Okay, let us see. When we look at this particular one, script 3, yeah, this is matrix multiplication logic. Okay, we are going to multiply this one S batch, test script 2.sh. If you multiply these two matrices with the help of one thread, that means one process, how much amount of time it is going to take? Much amount of this one is going to take. Okay, SQ. Okay, it is done. So the cat outputs. Here batch ID for job ID is 33118. MPI underscore job 3318 output. Here execution time is 0.55 seconds. Suppose here we are performing this matrix multiplication with the help of four processes. When we perform this particular simple matrix multiplication with the help of four processes, we can multiply that particular one. We can get that particular one. Here job ID is 3319. 3319. Yes, we can. We did it in 0.3 seconds, right? We can reduce the execution time. Are you with me? Are you with me?
Yes, sir.
Yeah. So this execution time depends upon many other factors. Okay. Here, actually, communication cost also plays a major role. Here, we are working with, actually, that means we are going to transfer the data between the processes, right, by using broadcast or gather, right? Okay, in that context, to establish a communication between these processes and to transfer the data between these processes, because definitely it consumes considerable amount of time. So while working with MPI, okay, we have to be very careful which data should be broadcasted and which data should be scattered. After that, how do we gather the data from all the processes? Are you with me? That is about MPI. Do you have any doubts? I will share all the programs with you. What can you do is you can execute these programs on your system or the server. If you have access to the any Perm supercomputers or any one of the computers from the institute from your institutes, you can execute these programs. Any doubt? Do you have any other doubts? I'm here to clarify your doubts.